Attendees are in listen-only mode.
Alright guys, welcome to the webinar. We're going to talk about Creo 2.0 Simulate. This is Sukumar. I work with customer-driven technology, and I have Sarah and Rosalinda with me. We're going to run a little poll real quick, and once we get done with the poll, we'll be on our way.
Okay, I'm going to go ahead and pull up the first poll question. Almost done, sorry.
No worries.
I'm going to go ahead and go to the next one. Sorry guys, I'm a little new to this, so.
That's no worries, sir.
Okay, we'll go to the next one. Okay, thanks everybody.
All right. So what we're going to talk about today is a few of these topics. Let me just change my slide real quick. There you go. We're going to talk about nonlinear stability. Okay. This is more of a snap-through analysis that you might find. We also want to show you how Simulate works with behavioral modeling and how without using Simulate you can still do FEA and see if you are optimizing for design changes. Next is understanding the convergence. A lot of people have asked me these questions earlier about, hey, you know, multi-pass, single pass, how do I read the summary file? You know, how do I make sense of what's coming out of the summary file? We will also talk about weighted links, welding, how to use the Pro Weld feature, end weld, perimeter, and spot welds. I want to show you something with respect to a preload situation. Preloads are possible in Creo 1 and 2, but it's not possible in Creo or Wildfire 5. We'll show you a workaround of dealing with that situation also. I have a few more things. If time permits, we'll go deeper into that. But these are the first 6 topics that we will be discussing. So, without wasting much time, let's jump in and look at nonlinear stability. So I have a cut section of a disk. Okay. If I go ahead and constrain the disk on the outer boundary here and apply a load on this side of it, on the inner boundary, if you look at the shape of the disk, what's going to happen is that it's not going to be a smooth deformation. It's going to deform for a little bit and then it's going to snap. To show you an example, let me just show you an animation of this, and we can go ahead talk about setting up this analysis. So you see how that snaps? So you see, even if you slow down the animation step by step, after a certain point, you don't get a result between those two positions. What if I want to know the result over there between those two positions? And that's where the nonlinear stability analysis comes into picture. Now, the reason you don't see a result over here. So first let's talk about the reason. Why don't you see a result over here? What's happening is that during the analysis, the force versus displacement graph kind of goes back down. See that? It's not always increasing. It kind of goes back into the negative side and then goes back up. So you don't see a result between that area. So how do you solve this kind of a problem, and how do you get results for say that area? So let's talk about setting this up. Now, I'm getting into simulate, and I'm going to solve this problem as an axisymmetric problem, right? Because it's symmetric about an axis. So we'll just go advanced 2D axisymmetry. We will select a coordinate system as a reference, and then we'll pick a surface as a reference. Now, in terms of adding material, you see, let's use steel. We can go ahead and create a mesh real quick. You see, it creates a single element mesh, shell element. If you choose to, which we will go ahead and refine the geometry. So I'm going to say edge distribution and say I want 4 nodes along this edge distribution. And now when I go mesh, you can see I get a few more elements. So next thing is to apply our constraint. So when it comes to constraints, you see that I want to constrain that top corner, and I'm going to let it translate freely in the X direction. Okay, that's my constraint. Then I'm going to apply a load at that bottom point right here. So basically I'm trying to simulate the load applied to the entire rim. Because we're solving it in 2D, I'm just applying it to that point. I'm going to say 2500 newtons in the Y direction. So that's my load. In order to calculate or find out the answer between the negative force versus displacement curve, we got to go ahead and create some measures. So let me go ahead and create a measure. Here I'm going to say this is for deformation. I'm going to use the drop down to get displacement, add a point, in the y direction, and that point is right there. So that's my deformation. Then I'm going to find out what is the reaction force. So you see the reaction force measure can be created from here. So let me just go ahead, name it reaction force, reaction at a constraint, and you want to know the y direction reaction, and then the constraint is right there. Now notice that the reaction is always going to be in the opposite direction, so to get the positive values for it, I'm going to go ahead and create another measure, which would be the negative or the opposite of the measure that we just created. So you can say negative of the reaction force measure. That's a computed measure. There you go. Let me get rid of this. Give me a second. Let me add that. Okay. So once that's done, let's go ahead and create our analysis. When you create the analysis, let's say we give it a name, snap through. That's your constraint, that's your load, and you want to go ahead and say nonlinear, calculate large deformation, because large deformation, right? And then you go ahead and say include the snap through. That's the checkbox that you want to be careful with. So make sure you check that. In the output, you can say use automatic steps, or you can go more manual and say, hey, you know what, I want user defined steps. And let's say maximum time is 1 second. So we'll divide that into 21 bitty pieces. So you see, at each step it's going to calculate all the detailed results. So I'm not applying load at once and say this is the end result. I want the whole process of gradually applying the load. So it's going to go ahead and calculate detailed results for me through it. Alright, so we go ahead and run the analysis. I have the analysis run already, so I'll go ahead and show you the results for it. Now, let's look at our animation. So you can see that it snaps through at that point because of the design, right? So what we can do is we can go ahead and plot a graph. So let's look at a graph with respect to a measure. So let's get a graph with respect to reaction force and deformation. So you can see how the force kind of goes down and comes back up. Instead of being all in the positive, it kind of goes back down negative, and you can get the values for each of the stress point through the analysis. This part of the analysis is where you don't get the result in the graphical interface, and that's why we use graph to kind of measure that, right? This is the nonlinear stability analysis that comes with Creo 2, and you can look at the measure versus measure graph in terms of reaction force versus deformation, and you can get detailed result. This is what's been eliminated by that animation from this point right here, from the peak over here to the same level over here. So this area's result you can find out through the graph. Alright, so that was our nonlinear stability. So make sure that you can create a nonlinear stability analysis, you can run it as a simple static stuff, but you need to make sure that you create these measures for your reaction forces. Now, the next topic I want to discuss is the simulate feature. So it's a very simple analysis that I'm going to run. I have this little plate. Get into simulate. You see that I have some constraints right here, and I have some loads right here. Now let's run a simple little analysis. We can look at the result for it, and you can see that this is what happens. All right, so as an FEA guy or the simulation expert in your company, you do this. Now, what you can do with respect to behavioral modeling and simulate is you can go to analysis, you can create a new analysis, you can give it a name, say simulate. You can pick the Creo simulate button right here, say next. You notice this is the analysis that we just ran. You'll go ahead and compute it. It's going to run through the analysis. All the results right there. You can pick up what you like. Say, for example, von Mises stress. I'm going to copy it. Say done. And you see it creates a simulate feature right here, analysis feature. If I want to know the value of my stress, I can just go to tree columns, feature parameters, and type in max stress von Mises. So there's the value. Now, let's say, hey, you know what, my allowed value is 110, and I want to kind of change the design a little bit, and I want to see what happens. So real quick, you can go into sensitivity analysis. You can pick a dimension, so you just pick and select the dimension. Let's say I want to go from 4 to 6. You see, what do you want to plot? I want to see how my von Mises stress changes, so I'm going to pick the von Mises stress right here, and I want to run it in about 4 steps and hit compute. So what it's going to show you is that as the round radius varies from 4 to 6, it's going to plot a graph and show you, okay, how does your stress change? So before you make a design change and before you go to the FEA expert and see what happens to it, you can see that, okay, even if I go to a value of 4, I am still not over my allowable limit. So you can find out if you're crossing the limit even before you make the change, you know, go through the whole process. So here you can see, okay, at the value 4, my stress value is 110 or less than that. So now what you can do is you can just go edit, make that 4, regen your model, and this should go ahead and update your simulate value right here. Just give it a second, it's running through it. And what I do is, because I don't want to run this analysis every time I regenerate, I just keep it suppressed. And when you keep it suppressed, you can also move it to the footer, so in that way it is always at the very end. And whatever features you add will go above the simulate feature. Right? So that was using the behavioral modeling to make design changes without having to know how to use or run the simulate. As soon as somebody sets it up, you can use that simulate feature to check and make sure that you don't cross over the design parameters in terms of stress or displacement or whatever you need it to be. All right? And you can always move it to the footer so that when you add new features to your model tree, it's not added below the simulate feature, it's added above the simulate feature. So all the feature changes are included in your analysis. The next thing we're going to talk about is convergence. So when it comes to convergence within Simulate, there are two types. One is a single pass and one is a multi-pass. So what is a single pass convergence and what is a multi-pass convergence? Here you notice that I have completely constrained the back surface and I'm adding a load of 100 pounds over here on this surface. Now let's go ahead, look at the single pass, constraint, load, single pass adaptive. Say OK, run it. You can look at some of the results that you get. Okay, so you can see the maximum stress is around the area where you have that little fillet. Okay, so let's look at the summary file. Summary file with respect to the simulate analysis. So let's go in and look at summary. All right. Even though it is a single pass analysis, you notice that Mechanica or Simulate actually runs two passes. Okay. In pass 1, all the element edges are at edge order 3. Now, what is element edge order? Now, the equation of a straight line is y equal to mx plus c, right? Now, y equal to mx plus c is a first order equation. Now, if Simulate has to match a curved geometry, then it will bump up the edge order to y equal to, say, for example, a square plus b square is equal to c. So you go to a second order. Now, if it is a complex geometry, it might jump up the element's edge order to, say, 3. In that way, it can go up to a polynomial order of 9. The advantage of that is that as your complexity in terms of geometry increases, we get an exact match to the geometric boundary with our mesh elements, because the element edge orders can match the geometric boundary shape. So what's happening here is that the maximum element edge order is set to be 3. It runs an analysis. It finds out the local stress errors. If the errors between two element edges adjacent to each other is more than, say, 10%, it will go ahead and bump up the edge order and run another pass. Now, how accurate is this? The analysis result between a single pass and a multi-pass are pretty close, like say within 5 to 6%, sometimes 10%. So what you have to be careful about when you run the analysis is the stress error and the percentage of the error. So I see that, okay, the percentage of the error is going pretty high to say 9.2%. So what can I do to fix this issue? Or how can I get the percentage of error in the principal stress to be less than that? Now, for that, we need to run a multi-pass analysis. Now, here in the multi-pass analysis, you see, you just change the drop-down to multi-pass. You get an option to choose the maximum polynomial order it can go to. I'm going to say the maximum polynomial order it can go to is 9. And the percentage of convergence is 5. And you see what it's going to converge on. So when you run this analysis, you get to find out how the element edge orders change. You see, it's running through the analysis real quick. We'll change certain criteria and you see how it improves. All right. So let's go back. Here is your summary file. Notice in a multi-pass, the first pass, all the element edge orders is at order number 1. Then it runs another pass with all the element edge orders at order number 2. It finds out the difference between the local stress error at element edge order 1 and element edge order 2 and sees if it is within the 5% that we were talking about. You see, this is the allowable error. And it's going to compare local displacement, local strain energy, and global root mean square stress. So it's going to take these three categories and it is going to compare the result for element edge order 2 and element edge order 1 and checks and sees if it is within the 5% that we have allowed. If it is not, then it is going to bump up the element edge order of selected edges up to 3. Then it is going to compare the results at pass 3 to the results at pass 2 and sees if it is within the 5%. So it keeps going on till it reaches where the results are within 5%. Now sometimes you have to also check for this. Elements not converged. Elements not converged is 12 of them. And elements or element edges not converged is 17 of them. So you can see how it's going to immediately go ahead, bump up the maximum element edge order to number 4. It runs another pass. It tells me that these are the number of elements that did not converge within the 5%. So you keep going till you see all zeros. Okay, it says all the element edge orders have converged. Right here, you see, goes to pass number 8, pass number 9. Now, whenever it goes through element edge order number 9, I am a little skeptical about the result. Why should you be skeptical about the result even though it says element edge not converged and elements not converged is 0? The reason you would be skeptical about the result is that you don't know if there was an element edge order 10 that was allowed, if it would have gone to 10 or not. So there is no sure way of saying that, hey, if I had allowable element edge order up to 10, it would have, if it stopped at 9, then you can say, hey, it could have gone to 10, but it didn't go to 10. So we can be confident about the result. Right now, because it went to 9, I am not very confident about the result. So you can see what you need to look for: the maximum element edge order and the number of elements and edges not converged. Next thing that you need to look at is the percentage. Okay, 2.5% is much less than 5% allowable, so which is a good thing. Next thing you want to look at, okay, we asked it to converge on root mean square stress and local RMS or global RMS and all these values. These are the values that we wanted it to converge on. So all these were good. But look at some of the other values. You see, for example, stress in XZ and stress in YZ direction. These have not converged. 27% is really, really big. So what would you do now? There are two things that you can do. You can go ahead and remesh. Remeshing is very easy. So you see this. I'm going to go ahead and say edge distribution. I'm going to pick a bunch of these edges. But before you know which area of the model to remesh, you might want to look at the result. Say, for example, you go look at this multipass result. And here, you see, instead of stress, you look at P level, and say, okay. You can see that this particular edge at the very corner, that element edge went up to polynomial order 9 at the legend over here. And you see most of your edges are at 8. So what I would do is go ahead and reduce or add more nodes or reduce the size of the elements in that area. So this is what I'm going to do. Let me go ahead and refine the mesh. For some reason it keeps me kicking out of this. So I go ahead, say edge distribution. I'm going to pick all these edges wherever element edge orders were 8 or 9. It's not necessary. I'm just picking everything because of time constraint. So I'm just picking everything instead of running multiple analysis. So you can see I picked all these edges except the one on the bottom. There you go. And say I want at least 5 nodes on it. And then I can remesh it. So you can see I have much smaller elements right now. And then we will rerun our analysis. Now, another thing is that you notice that how maximum stress YY did not converge and maximum stress XZ did not converge. So what I'm going to do when I set up a new analysis, say multipass, oops. I'm going to go here. Maximum edge order I can go to is 9. Percentage of convergence is 5. Now instead of converging on local displacement and global root mean square, I'm going to go pick my own measures. So I can go ahead and say, I know U2 did not converge. So I'm going to add them and say converge on those results. So I'm forcing it to converge. And that's how you would run a convergence analysis. So here I'm going to go ahead and run this one real quick and we can see the results for that. Now, as you remesh and as you add more stricter criteria, you have to also keep in mind that it's going to take a little bit longer to run the analysis. Now, you see this was your result. You can see the number of passes it ran. Number 1 pass, 2. Right here you see the number of elements not converged. You see here there are a bunch of elements not converged. And you have to also notice that your displacement and your maximum stress XY, these two were not converged. So you'll go ahead, edit that and add those two measures. So displacement Z and I'll just add all of these because I can keep running multiple analysis to go step by step. I guess we get the point here that it is better to add the criteria that we are more interested in as a convergence criteria. Now it would take a little longer to run the analysis as we are forcing it to converge on multiple parameters. So let's go through this. Now it's at pass number 6. You see that, even though it could have gone to element edge order 9, it stops at 6. All our elements have converged. You see the percentage of error in the principal stress. We can scroll down and look at all of these. You see one is exactly at 5. Fair enough, so it's still 5%. Now this result would be your best result because now you can say for sure that you have all your parameters converged within a certain percentage of value. You do not have any of the elements not converged. You did not go to edge order 9 or more, and your principal stress is also within your limit. So whenever you try to justify a result, you want to make sure that all these things are taken care of. Then you can say, hey, you know what, I can be for sure that this is a very accurate FEA. So that's how you would read the summary file, and we spoke about how to force converge it on certain parameters, which we did. All right. Now for the result, you can also use it as a comparison. Now you look at the comparison of the multi-pass, and let's go and compare it with the single pass. So you can see maximum displacement Y, maximum displacement X, displacement magnitude. It's not a whole lot, it's 10 to the power minus 5, so it doesn't really matter as much. But if you look at your principal stresses here and your von Mises stresses, and your principal and von Mises stresses, instead of being 250, it's 270, and instead of being 230, it's 247. So you can see that the single pass comes pretty close to a multi-pass in terms of accuracy, but if you want to be 100% sure, you would go ahead and run a multi-pass analysis. Next thing is, when you set up an analysis, you also want to look at the output tab and look at this plotting grid value. Now, what is this plotting grid value? Let's look at a result file and I can show this to you. So let's look at this and get a p-plot. Now, this is your element, right? These are your mesh. So when you say the plotting grid value is 4, what it does that most of the FEA solutions, or the way the theory is programmed, is it's programmed to calculate the values at the nodal points. Nodal points is when bunch of element edges meet. Now, when the plotting grid is set to 4, Mechanica will not only calculate the value at the nodal points over here, but also at 4 locations along the element edge. Along each element edge, it will calculate it at the ends as well as 4 locations. So in that way, you don't really have to make the mesh very, very small to get a more detailed localized result. If you increase the plotting grid from 4 to say 6, it's just that what you're doing is you're calculating the answer here at the end, and 6 different locations along the element edge, and it does that for each of the edges. A good value to have is the default value, which is 4. You can choose to go up to like about 7 is a decent number if it's a very, very critical part. But you have to also understand that if you increase the plotting grid number, it's just going to take a lot more time to solve the problem. All right, so that's what I had about convergence criteria and how convergence works. I don't know if you guys use ProWeld. ProWeld is a free feature. It comes with ProE. So if you are in the assembly mode, you go to welding. You see that? You can create this ProWeld. Now, what I'm going to do is I'm going to go ahead and suppress it and say, hey, I want to create a fillet weld. So I'm going to go ahead and pick a bottom surface and pick that. Oops. Side 2 would be that. And then I can create my weld. Now you can also go intermittent if you want to. So you can see I want 20 of them and I want the width to be 3. So you can see you can get intermittent welds or you can get a full weld. Just like this, you see that you can also add material. So you see weld material, I want to define the material to be steel, or you can choose it to be whatever you want. You see it creates a symbol that you can show in your drawing. Here are all your properties, you can define them. Parameters, if you want to call out at different places, you can do that. It's a very easy way to create your welds and create these symbols that can be shown in your drawings and can be controlled from a 3D part of it. Now, if you create this weld, when you get into simulate, all you need to do is you'd go weld, weld feature, and select the weld feature. All right. So now this will read directly from the thickness and all the other parameters from the weld feature, or you can override all of them and change it to whatever you want here. So you don't have to recreate the welds again. If your assembly has welds and if your design people are creating the welds, you can just use the same welds in simulate. Okay? So in that way, you don't have to recreate them. Now, With respect to welds, there are some other types, say for example, perimeter welds. So if you have two plates and you want to kind of weld around it, you go to the weld feature, you can say perimeter, you want to select the base to be that, you want to select the doubler to be the bottom surface right there, and then you want to select the edges. And then you can enter, say, thicknesses 2. It goes ahead and creates a weld over there. If you go ahead and do an auto jam, you see that it's adding that weld feature here, but there is no weld feature over there. See that? You can see clearly there is no weld over there, but you see those two edges, you have that extra element which acts as a weld. The only trick or confusion that happens most of the times, I get the questions like this, is you need to make sure that the bigger surface is the base and the smaller surface is the doubler. So if I remove that, you see you have a doubler. If I choose the base to be the doubler and this to be the base, you see that the edge that I get to pick is that. I cannot pick that edge. You're always picking the edge of the doubler plate and not the base plate. So you need to make sure if that's where you want to weld, you pick the bottom surface over there as the doubler, you pick the bigger surface as the base, and then you can go select the edges, enter thickness, and say OK. That was perimeter weld. Spot weld. If you guys use spot welds, or if you have a need for it, there are a couple of things that you can do with a spot weld. So let's say, anytime you want to create a spot weld, you want to create datum points on either side of the plate. Let me go to my view and turn my tags on. You can see those are my datum points. I have one datum point on the bottom surface and the other datum point on this other part's top surface. Another limitation, I would call it, for a spot weld is that both the plates need to have a gap. You cannot make them stick to it and create a spot weld. Now let's go first create a spot weld. I'll show you why there needs to be a gap. So in the simulate feature, let's go to weld. We'll use a drop down to choose spot weld. Here you can pick the top surface over here and the bottom surface of the plate. You see the two surfaces that we have picked. Then you can select them points. Now when you select the points, you can go one by one, or you can just drag a box like that. See that? You can enter a diameter and material. And you see what you basically get is that. See that? That's a spot weld. Let me go to a no hidden line so you can see that clearly. You see that's a spot weld. So what this spot weld basically is a beam element between those 2 points. So using the 2 points as a reference and creating a beam element. Now if the gap between the 2 points is 0, or if the plates are touching, the length of the beam element would be 0 and you cannot create it. So see, I'm going to do something very similar on this side. So I'm going to say beam. I'm going to say point to point and pick the 2 points. I'm going to create a beam section, and here let's choose a circle of radius 5. Let's look at a coordinate system. Yeah. So you can see that's basically a beam. This is exactly what the spot weld is. Except that, you create it to a different interface and you don't get to choose the cross-sectional shape or size. So the reason there needs to be a gap between the two plates is that the length of the beam would become 0 if there is no gap. Okay? So please make sure that you remember to have a gap between the two plates if you are doing a spot weld. Okay? If you're not interested in a spot weld and you can just use beam to simulate it, the results are very, very close. You know, I would say to the 100th close. All right? So that's spot weld for you. Make sure you always create or maintain a gap between the two parts. Another thing is weighted links. Now say for example, I have this little assembly and I have a huge load sitting on these four surfaces on the top of it. Okay. Now I want to see the stress that's applied towards this little sheet metal part or assembly. Now instead of modeling the whole load on top of it, what you can find out the center of gravity point. See that CG point right there? You can find the CG with the load on and create a point over there. So now when you go into simulate, first thing you're going to do is you're going to go ahead and put a weight on it, right? So mass at that point and say, hey, you know what, this is about 1,000 pounds. Then you see there's a mass right there, mass 2,000 points. Then we go weighted link, we pick surface, we're going to pick those four surfaces on which our weight sits on top of and say the dependent side is that point. So what's going to happen is that 1,000 pounds of load is going to be distributed on those four surfaces. That is a weighted link. So instead of you modeling this heavy piece, meshing it and doing all kinds of stuff with it on top of this hopper, you can just put a load of 1,000 pounds on the CG point and then use a weighted link to distribute that load on that surface. All right. Next thing I want to talk about is preloads and how preloads can help you. What if you don't have Creo 2? How will you simulate a preload? So let's get to this. I have this little assembly. All right. Now, let me make a section of it. And use a different color. So you can see that you have a sleeve right here. You have a sleeve. You have a bolt. You have two plates. And then you have a nut. Okay. So when you tighten the nut, this bolt is in tension. It's going to try to pull the two plates right here, this plate and the bottom plate. See both these plates? It's going to pull both these plates together. When that happens, the sleeve is going to resist it. So here's your sleeve part. This part is going to resist that force. So what's going to happen is the sleeve is going to be under compression, the bolt is going to be under tension. Okay. Now, if you want to simulate this in Creo, all you would do is you'll go to simulate. Now, I'm going to go ahead and hide the sleeve part just for display purposes. You notice that in the bolt part, I've created a volume region. See that little volume? So what I can do is I can say preload, pick that volume and say, hey, you know what? I have a preload of 1,000 pounds. And I can easily solve the problem. Now, what if I am not in Creo 2, I'm in Wildfire 5, and I have to solve the same problem? Okay. Now, there is a workaround to do that. Notice that I'm going to play with the material right here. So you see I have a material steel. You see the coefficient of thermal expansion right here. I have a copy of steel where I don't have a coefficient of thermal expansion. That means if I apply this copy of steel material to any part, even though I heat it or cool it, that part's not going to be affected by the temperature change because the coefficient of thermal expansion is 0. Now, what I've done here is that you notice the whole assembly gets copy of steel. Copy of steel does not have coefficient of thermal expansion. That means even if I heat or cool it, nothing's going to happen to the rest of the part. Then I have another material assignment where I select this particular volume and I apply the material steel. This material has coefficient of thermal expansion. So when I cool this whole assembly, what's going to happen is that this bolt or this area is going to shrink. So when that shrinks, it's going to put the bolt in tension. And when the bolt is in tension, it is going to push down on this block and push down on this block, and you'll have the sleeve under compression. Now the theory is that you know how to solve the stress or a load in a bolt, a force by area. You can also use temperature and coefficient of thermal expansion to get the same kind of preload. Okay, so what I'm going to do is I'm going to say temperature load. I'm going to say the load value is say minus 60 because I want it to shrink. The current temperature is 30. So the room temperature is say 30. I want to shrink that area to minus 60. So how would I know if I want to put 1,000 pounds of preload, what temperature should I use? So the force by area thing is same as the temperature times the coefficient of thermal expansion. So you can match easily and say if this is my coefficient of thermal expansion, this is how much temperature that I have to add to get the same kind of load or stress on it. So once you do that, you just constrain the part. Load, your load is the thermal load right here. So you can see load is the thermal load. If you go ahead and run this analysis, you can see what you get. You get this. So you see everything's happening inside the part, though I have to kind of like hide a few components, which I can very easily do by going to the display location, components, you pick the sleeve, and you hide it. You can see I don't really care about that part of it. I want to see how much stress that part's going to put on my part. So let's go ahead, show everything, and we'll slice it out so that you can see what's happening inside. So let's not animate it. And we'll use the cutting capping surface. So you can see when that shrinks, see that part of the bolt is under stress, and then your sleeve is going to compress. Okay, so you can run the get the result for individual components very easily. You just go here, say show everything, and pick the sleeve. So you see getting rid of that. Let's hide everything and show only the sleeves. You see the sleeve is kind of compressing. You can go ahead and animate that result if you want to. You can see how the two plates are pushing on that sleeve. So basically, you're tightening the bolt, you're tightening the bolt, and then the sleeve is under tension, and the bolt is under tension and the sleeve is under compression. So you can look at this. So when this shrinks, the bolt and the nut push down on the plates push down on the sleeve. So that's a way you can work around. Now, if you don't want to do that and you have Creo 2, it's very simple. You just go ahead and say preload. Here's your preload, pick a volume, enter 1000. But then if you don't have Creo 2, you can do the same thing that I showed you with Wildfire 5. So that's pretty much what I had. These were some of the common tech support questions that I've been getting about convergence, using behavioral modeling to do simulate features, some of the welds and weld links, and the nonlinear stability was also most frequently asked question, so I wanted to show that with you. In that way, I don't end up repeating what I've already shown in the earlier webinars. All right, so that's it from me, guys. And if you guys have any questions, just feel free to ask. Rosalinda and Sarah, you guys there?
Yes, we are.
All right.
I'm not
so
seeing
we'll
any
give about
questions.
5 minutes for
Yeah, well, we got about
question
2
and
minutes.
answers.
Yeah, 2 minutes, and I'm not seeing any questions yet, so we'll give it about a minute in case anybody thinks of one, and then we'll shut it down.
Okay, I'll leave my contact information right here. So that's my email. You can call me for any questions regarding this subject. With respect to training, you can always contact Rosalinda. And Sarah is the organizer, so you can keep in touch with her in terms of new topics or whatever it is. Okay, I think I have a question. Is there any diagnostics to run errors? Yes, sir. When you run an analysis, it will say, do you want error detection? So when you run the analysis, it's going to kind of tell you, hey, you haven't defined material. There's an issue with your mesh. Things are not connected. You have a diagnostic utility which is going to go ahead and tell you what's wrong with it. Does that answer your question, Kevin? Is that Kevin? I want to make sure it's Ken. Does that answer your question, buddy? Just say yes if you. I don't know if you're muted or not, but can we unmute everybody? Okay, no run failures. Can you let me unmute Ken and can you talk now, Ken? Can you speak up, please? I unmuted you.
Yeah, we're here. Thanks. What
Yes,
we're
sir.
talking about is when you're running an analysis and it basically just crashes and it says, ended due to run errors or run failures. Will there be any kind of diagnostics to say it was this node or this volume interference or things like that, or radiuses?
Yes, sir. Yes, sir. Whenever you get that error, you have to go ahead and open the model in the independent mode of Creo Simulate. When you install Creo Simulate, I don't know if you can see my screen right now. Let me go to Creo, and you see you have these legacy. When you open this when you open the port in this particular software, which is free, it comes with it, then you get to see the exact node and the details. Now here you have to think about this. Whenever there is an issue, okay, it throws out an error. You have to think about, say for example, let me get my paint going. See, it is force is stiffness times displacement. Fair enough? So you're going to calculate displacement equal to, it is a matrix, so you do a K inverse times D, or K inverse times F, my bad. Okay? This K matrix is singular. That means it cannot be inverted. Okay? So if it cannot be inverted, how are you going to solve this problem? You cannot solve the problem, correct? So by default, a K matrix is singular. When you add constraints to your model, certain rows and columns in the matrix are removed and it becomes non-singular. When it's non-singular, it becomes invertible. Fair enough? And hence you solve it. So most of the times your errors are also like insufficiently constrained. Right? So when it's insufficiently constrained or some of the elements have a problem, you cannot go back and look at the matrix, which is like about 1,000,000 by 1,000,000, and find out which particular area has a problem. That is why anytime you call tech support or whatever and you ask them, hey, you know, my part wouldn't solve, they'll say, oh, you need to refine the mesh. So basically what you're doing is you're thinking like a programmer. What are you doing when you refine the mesh? When you refine the mesh, you change the numbers inside the K matrix. Okay? So with the same constraints, with different numbers, maybe the K matrix is invertible.
Okay.
You see what I'm saying?
Yeah.
So it's not, whenever it says insufficiently constrained, it doesn't mean that your constraints are wrong.
In the mesh, they don't detect those constraints.
Yeah. Okay, well that was helpful.
Okay. And you can send me an email if with any of the screenshots you might have or whatever it is, and we can work on it. You know.
Okay.
I'll put up my email right here. You see, that's my email. We can go back and forth, exchange emails, whatever it is.
What if I got it?
All right, Ken?
Yes, thank you.
All right. Any other questions, guys? Sir, I think that's it.
Okay. Well, thank you for attending, everybody, and we'll have another one next week, and it'll be posted. There'll be another email blast going out to let you know what it is, and this will also be on YouTube later today.
All right. Thank you, guys.
Thank you.
Thanks.
Bye.
The organizer